Hello students, I hope you are doing well on this weekend. I apologize for the poor audio quality of this recording. I managed to accidentally leave my boom mic at school, so I'm having to use the internal microphone on my laptop, and the quality is not as good, but I'm sure we'll survive. So let's get started. Our final topic that we have to discuss is the idea of what are called asymptotes. Our objective is the student will learn the basic vocabulary and appearance of asymptotes in graphs. The date for Monday's class will be October the 7th. As always, copy down your objective and your date, and if you need more time, press pause and then hit play when you're ready to move forward. Alright, your basic definition for an asymptote is that it is a line that a graph will approach as it runs to infinity, but it will not touch. Essentially, it acts like an imaginary boundary. Now, if you get to thinking about the types of graphs that you've seen over the years, if you apply this definition, you may find that you have seen asymptotes for years, but may not have realized that they had an actual definition or any type of an application in the graph. But we are kind of getting into something new, so I'm sure you will recognize the asymptotes now that you see them. Now, there are three basic types of asymptotes that we are going to run into in graphs. Their categories are horizontal, vertical, and oblique. Oblique is a fancy word that means slant, and you will actually see this word both ways in problems and in graphs. It just seems that some people prefer the word oblique, some people prefer the word slant. You will see it both ways. There's no telling which way it will be. However, the term that I use is oblique. So here are some basic diagrams that show you kind of what horizontal asymptotes and oblique asymptotes and vertical asymptotes will look like in a graph. Basically, the idea is that the graph is doing whatever it is that the graph is doing, but then as numbers become larger and larger and graphs try to run to negative infinity or positive infinity, they approach a particular boundary line, but they never actually reach it. And that's kind of a difficult concept for a lot of people to get their brains wrapped around. It seems like, common sense would tell you that if you get closer and closer and closer to something, that if you go to infinity, you will eventually actually reach it. And unfortunately, in mathematics, that's not exactly the case. You can get infinitely closer and closer and closer to something without actually ever contacting it. That is the premise that an asymptote is based upon. Getting closer and closer and closer to something, but never actually making contact with it. Okay, so all we're going to do is we're going to take a look at some basic examples to get our feet wet here. Now, the equations that you will see will be, in some cases, fairly complex. It just depends on the type of function, as does everything depends on the type of function. Okay, so we're going to start off with this one. Considering the following equation in quadrant 1 and see if it has any asymptotes. And our function is the reciprocal of x. Now, if you have no idea what the reciprocal of x looks like, well, we're going to follow the same procedures that we did the other day. We're going to graph some points and we're going to see what's going on. But we're checking out the reciprocal of x to see if it has a horizontal asymptote, to see if it has a vertical asymptote, to see if it has an oblique asymptote. And as you will discover, some of these asymptotes can show up in the graph at the same time. It's not like a graph will have one or maybe one of the other two. It is possible that it may have two at once. Not actually possible to have three at once, but we'll get into that a little bit more for Tuesday's class. As I said, if we're not really familiar with the graph of the reciprocal of x, then what we will do is we will pick our points in the domain, just like we did on Friday. and we will plug them into the equation to see what the range is doing at those particular points in the domain. So for this particular graph, we have domain points of 0 through 7, and clearly as we plug these into the function, those will put them in the denominator, so we will have 1 over 0, then 1 over 1, and 1 over 2, and so on. Now clearly we're going to end up with a problem when we plug in the very first point in our domain, 1 over 0. That's going to place a 0 in the denominator of our fraction. There's nothing more that we can do to simplify it. Okay, so we end up with an undefined value right off the bat. We'll talk about that more here in a moment. But when we plug in the 1 and the 2 and the 3 all the way up through 7, we get some decimal points that should be easy for us to plot. Now let's look at those first two ordered pairs in the XY chart. We've got 0, comma, undefined. Okay, clearly something is going on at 0 in the domain. But once we get to 1 in the domain, the graph is just fine. We get to a point of 1, comma, 1. So what we may want to do is look at what is happening to the graph in between 0 in the domain and 1 in the domain to get a better idea of what the graph is doing. So that's exactly what we'll do. We'll pick on some fractional values in between 0 and 1. Okay, well there's the points that we have graphed so far. But clearly we need to kind of know what's going on in between 0 and 1. Based upon the way the graph is behaving, we might suspect that the graph is going to turn upward and move along the positive y-axis. But let's take a look. We're going to invent some values in between 0 and 1 along the x-axis. I've chosen 1/4 and 1/2 and 3/4. We can always choose more if these are not enough, but these may be enough to give us a general idea. So once again, we'll take these fractional values and we'll plug into the denominator of our function, because that's where our x value is, and we'll get y values back from it. Taking these ordered pairs and plotting them into the graph as well, we get these points. Okay, very clear to see what's happening in the graph. Our suspicions are confirmed. The graph is turning upwards as it approaches the y-axis from the right side. Okay, so I believe we can probably answer our three questions there. Does this graph have a horizontal asymptote? As we move to infinity in either direction, is the graph approaching a horizontal line that it is likely never to touch? It does seem true that the x-axis is a horizontal asymptote. These points will get closer and closer and closer to the x-axis, but no matter how big the x value is, when we continue to plug it into this denominator, it does not actually ever reach a value of 0. So the range never goes to 0, the points never hit the x-axis. So yes, the horizontal axis is an asymptote. How about a vertical asymptote? Seems pretty clear that the graph is turning upwards exponentially as we move from right to left in this graph. Okay, and we can kind of experiment with this a little bit if we're curious. We can get smaller and smaller fractions getting closer and closer to the y-axis, but we will find that the graph never does actually make contact with the y-axis. X never goes to 0. So we will end up with a vertical asymptote. Now, does it have an oblique asymptote? Meaning, is there a slanted line that runs through the graph that the points are trying to follow along? Seems pretty clear there is no such thing in this graph, but we'll look at some more here in a moment. But in this graph, there does not seem to be any type of an oblique asymptote. Okay, let's take a look at a different function for a moment. Consider the following equations in quadrant 1 and see if it has any asymptotes. This time our function is a rational expression again, meaning it has a numerator and a denominator. This time the numerator is x squared plus 1, the denominator is x. So we're going to run through the same process again, trying to answer the questions. Do we have a horizontal asymptote? Do we have an vertical asymptote? Do we have an oblique asymptote? And in order to kind of discover that, at this point we need some points so that we can see what the graph is doing. So once again, we're going to invent domain values that go along with what our graph offers us. Okay, we have 0 through 7 in the domain. As we plug into this function, as you can see in this function, each x value has two different places to plug in, one in the numerator and one in the denominator, and that makes it a little bit more complicated for us to figure out the range values, but it's still basically just junior high math, plugging in those values, simplifying the fractions, and when we do plug those in one at a time, we end up with these values. Once again, we can see that in the domain we have a problem when x is 0. That caused the denominator of the fraction to be 0, so the range is undefined. The rest of the values are okay, and when we plot them, we end up with this. But once again, we'd kind of like to know what's going on in between 0 and 1 in the domain. It looks like, as you read this graph from right to left, it looks like the graph is starting to turn, possibly in an upwards direction, as we move from 2 in the domain to 1 in the domain. Sure would be nice to know if it did anything beyond that. So again, we will invent a few values in between positive 1 and 0 in the domain, and then see what the graph actually does. Okay? So on those values, we would end up with these range values when we plug in the domain. Plugging in those points into the graph, we end up with these points. So once again, it seems like our graph is going to follow a couple of asymptotes here. Is one of them horizontal? No, there's no indication of a horizontal line that these points are following. How about vertical? Yes, just like the previous graph, this one does seem to be following a vertical asymptote on the y-axis. And this time an oblique asymptote, a slant asymptote. Yeah, these points do seem to be lining up along a slanted line, so this one does seem to have an oblique asymptote present. One final example. Consider the following equation in quadrant 1 and see if it has any asymptotes. This time the function is 2x plus 1 over 2x. We're going to attempt to answer the same three questions again. So once again, we will need some values in the domain that we can plug into the function and get our range. We still have 0 through 7. When we plug in these values into the function and get our corresponding range values, these are the values that we end up with once again. Okay. Again, for the third time, we see that we do have a problem at x equals 0. Okay, so we will need some additional points. Well, here are the points that the 1 through 7 did bring us in the domain. And if we ask the function about what is going on between 0 and 1, and again, I've selected the same three values. When we plug in these three into the function, we end up with these values, and that adds those points to the graph. Okay, so let's see if we can figure out, do we have a horizontal asymptote? Is there a horizontal line that the graph is approaching? Sure does. Seems like y equals 1 is a asymptote that this graph is approaching. Vertical asymptote, is there a vertical line that the graph seems to be approaching? I believe the y-axis is going to be a good vertical asymptote. And the oblique, is there an oblique one, a diagonal or a slanted line that these points seem to be approaching? Cannot identify one in that. Okay, so it looks like we will have a horizontal and a vertical asymptote in this one, but nothing else. That is the basic idea of asymptotes. Next time we will look into them a little bit deeper, but as for today, that's all we need to know. What are horizontal and vertical and oblique asymptotes? So that should be enough information to get us started. I'll see you in class on Monday.